Newton's first law, was an object in motion stays in motion, an object in motion stays in motion, and an object at rest stays at rest unless acted upon by an outside force. Acted upon by an outside force. Okay, so this is one that you interact with on a continual basis, but most notably when we talk about riding in a vehicle. You have all at some point, I hope, ridden in the backseat of a vehicle next to someone, right? And when you're in the backseat of a vehicle riding next to someone and you go around a curve, what do? Right, you lean into them hard because you're being thrown to the outside of the car, and so you exaggerate it, squishing them against the door, right? Everybody does this? You're normal people? Okay, good. So if we've got our car here with its wheels, and our car is going around a curve, why are you thrown to the outside of the car? Because you're still going straight. So that's the right answer. The usual answer that I get is because you're thrown to the outside of the car by a centrifugal force. No, that doesn't exist. Centrifugal forces aren't a thing. But you are thrown to the outside of the car, or rather you feel like you're thrown to the outside of the car, because while you're going around the curve, your body is trying to go in a straight line at each different point. However, the car is turning underneath you. So as the car turns underneath you, from your frame of reference, it feels like you're thrown to the outside, when really everything else is just trying to apply a force to you to get you to keep turning. So as your car turns, you try to keep going straight. To go straight. That is until an outside force has applied to you. And that outside force is typically friction between you and the seat or the car door itself. This also applies if we're talking about seatbelts. When you slam on the brakes, what does your body want to do? Keep going forward. So you need something to stop your body. Seatbelts are the wise decision for that. If you slam on the brakes and you don't have a seatbelt to stop your body to apply that outside force, you get to pick. You get to have either the dashboard or maybe the windshield or the curb outside, apply that force and get you to come to a stop. So obviously there's a whole physics reason that we could talk about seatbelts, and we will later on in the season. All right. Questions about how Newton's first law applies here, or what it is. Okay. The next part about this is we use the term here, force. We need to actually identify what that is. So a force, I'm sure the book has some fancy definition with way more words than it needs, but simply put, a force is a push or a pull. A push or pull. All forces are measured in newtons. Alternatively, if you're in the terrible English system, we could talk about it in pounds. And they are a vector unit. So measured in newtons, which is abbreviated N, and is equal to, so 1 Newton is equal to 1 kilogram meter per second squared. So mass times an acceleration. We'll get to that in just a moment. Actually, we'll get to that now, which is Newton's second law. So in the book, if you happen to have missed it, we heard that force is mass times acceleration. Now they do clarify here just a little bit. They say the net force is equal to mass times acceleration. So when we talk about the difference there, a net force is the sum of all forces acting in one dimension. Not every individual force is just automatically equal to mass times acceleration. It is only the sum of forces acting in a single dimension. So a net force is the sum of all forces acting in a dimension. acting in a dimension. And Newton's second law simply states that force net is equal to ma. Now, the way that's written is actually a little bit misleading, so we're going to rewrite Newton's second law in a slightly different manner. When read this way, Newton's second law indicates that the mass times the acceleration, these are kind of independent variables, that we can determine the mass, we can determine the acceleration, and whatever that product is the net force that must have been applied. Well, really, if we rewrite this as acceleration is equal to the force net over the mass of the object, we're reassigning what the implied independent variables are here. The implied independent variables then are the net force and the mass, and the acceleration is the dependent variable. And that should be how it's read because the acceleration is really just how an object interprets a net force. Acceleration is how an object interprets a net force. All right, so I'm going to scoot this up just a bit. All right, for example, let's say we've got a box. And this box is sitting on the ground. What forces would be acting on the box as it sits on the ground? Gravity, there's the easy one. All right, a few things about gravity. First of all, I'm going to mark it as Fg. Force of gravity, Fg, is always equal to the mass of the object times gravity, where gravity is the local acceleration due to gravity, or 9.8 for most of our situations. If we're on a different planet, it's a different amount. One of the mistakes I see students make all the time is I say, what's the force of gravity acting on this object? And I hear a response, 9.8. That's an acceleration due to gravity, not a force. If I'm finding a force of gravity, it's mass times 9.8. Okay? If I ask how much is the force of gravity, and you just tell me 9.8, you just told me that Emily and I have the same weight. I'm going to go ahead and say no. We do not have the same weight. We do not both have a force of gravity of 9.8. If we do, well, then I am definitely deceptively large. In order to talk about force of gravity, we have to multiply it by the mass. Okay? Don't make the mistake of just saying that gravity is the force of gravity is 9.8. That's just the acceleration. All right, so we've got a force of gravity here. What other forces are acting on this box as it sits on the floor? The ground against it. Without the ground against its force, this object better fall through the floor. Typically, we call this force normal. A normal force is a force that exists between two objects and acts perpendicularly to the plane of contact. A force that acts or that exists between two objects and acts perpendicularly to the plane of contact. Okay, so we've got our normal force. All right, Todd has decided that this box is in the wrong place, so he's going to push it. Okay, pushing this box, we now have an additional force that we can indicate here, and that would be an applied force. Force A for force applied. Alternatively, if you want to label that FT for force tied, go for it. Okay. Applied forces are just other pushes or pulls. There's no special definition for them. We just happen to have that one acting there. Now that I've got that applied force, there's one more force that I have to indicate on here. What could it be? Okay, but I'm only interested in the forces on the box right now. We can come back to that one. Say it louder. Friction. So I've got friction acting back here. Friction. Friction is a force that exists between two objects that inhibits motion and acts parallel to the plane of contact. A force that exists between two surfaces and acts parallel to the plane of contact. We can break down friction into two subcategories. Anybody remember one of the two subcategories for friction? Anybody got a guess? Static friction. Okay, there's one. Static friction. Static friction is the friction that exists between two objects that are not moving relative to each other. Exists between objects not moving relative to each other. All right, I saw a couple other people who are ready to offer me another one. What other examples of friction or types of friction do we have? I'm going to come back to that one in a bit because that one's frequently categorized in weird spots. Anybody got a third one? Dynamic friction. So dynamic friction is the way we typically frame it in engineering courses. Typically in physics, we'll call it kinetic friction. It's the same thing. So kinetic friction. Kinetic friction is the friction that exists between objects that are moving compared to each other. Exists between objects moving relative to each other. All right, so examples of these friction. Rolling friction at this point, because frequently rolling friction gets miscategorized as a version of kinetic friction because of the same reason you guys said that I was experiencing kinetic friction when I walk, because the objects are moving. But if we think about a tire, the point of contact of a tire and the road don't move relative to each other when they're in contact. Therefore, they experience a static friction, unless, of course, you're peeling out. So the static friction is where rolling friction should be categorized because of how the point of contact between the tire and the road don't change relative to each other. So rolling friction is kind of a subcategory that gets debated between these two. All right, questions on any of this so far? Sure. So if I take a step, I'm going to pull back on the ground. When I pull back on the ground is what's going to actually push me forward. So I'm pushing backwards on the ground, and then by Newton's third law, we get our movement forward. So Newton's third law. What is Newton's third law? For every action, there's an equal and opposite reaction. All right, action, ball, I'm throwing it. What's the reaction? Say again? I hit it in the ground. How is that equal or opposite to me throwing it? Okay, I threw it that way, it bounced up. Forward and up don't seem opposite to me. And the answer to it is they're not. Newton's third law, as for every action there's an equal and opposite reaction, is actually very poorly worded. Really, to understand it conceptually better, we want to take a look at how it's stated for babies. For force, there's an equal and opposite reaction force. So action and reaction are too broad of a term. If we narrow Newton's third law down to for every force, there's an equal and opposite reaction force, then we recognize that we're only talking about forces. So when I threw the ball forward, what was the force that acts equal and opposite to me throwing? Right. The ball exerts a force on my hand. So if we think about this in terms of standing in a frozen pond with skates on, you come up to your friend and you're going to push them in the back. They're going to go forward, but what are you going to do? You're going to go backwards, meaning that when you push them, they push back on you, even if you push them in the back and they didn't see it coming. Okay? So for every force, there is an equal and opposite reaction force. All right. Questions about that idea? And what I would like you to do is take another look at this free body diagram. Hey, look, we're going to put a term on this. This is a free body diagram. A free body diagram is simply a picture where we label forces that are acting on it. Okay? For this free body diagram, I want you to pick out the equal and opposite forces for each of these four. Okay? So determine what the equal and opposite forces are for each of these four forces that are acting on the box. All right, so how many of you picked force gravity and force normal as equal and opposite? And how many of you picked force applied and force friction as equal and opposite? Okay, neither of those is right. Neither of those is right because when we talk about Newton's third law, we aren't talking about just one object. Newton's third law indicates that forces and reaction forces exist between objects. So I think, who talked to me earlier about the person here? Getting a force exerted on them. Okay, Mark. So you had said that when they apply a force to the box, what? Right. The box applies a force back on Todd here. So Todd feels a force backwards. Force to the box. Nishi, you had said that, well, if the force applied and the force friction have to be equal and opposite, it can't accelerate forward, right? And, well, if these were equal and opposite, nothing could accelerate ever. That's not the case. Because the forces exist on different objects, we can get those accelerations, and those forces can be equal and opposite. So this force here is equal and opposite to this force here. So as Todd pushes on the box pushes back on Todd. It's why if you walk up and just punch a wall, it hurts your hand because the wall punched your hand. Okay? It exerts the exact same amount of force on your hand as your hand did on the wall. Okay? Force of, let's go force normal. What is exerting force normal on the box? Earth, or the ground, right? So if the ground exerts a force up on the box, then what must also be true? Right, the box exerts a force on the ground, force normal. And I'm going to go ahead and highlight that in orange. Okay, next up, force friction. Force friction, what's exerting force friction on the box? The ground. So the box must try to push the ground the other way, force friction. And I'll put this one in Sharpie, I guess. All right, lastly, what causes force gravity on the box? Mass, specifically the mass of what? What causes force gravity? Earth. Earth causes force gravity. So if Earth pulls down in the box, what must also be true? Yep, keep saying it. The box pulls up on the Earth, yes. Right? So if you jump up into the air, yeah, Earth's going to pull you back down, but you're also pulling back up on Earth, so it accelerates towards you. Now, the mass of Earth is incredibly large, so that acceleration is incredibly minute and doesn't really matter because it's so small, but it does exist. As you jump up into the air, Earth is going to accelerate towards you as you accelerate towards it. We can see this is true if we talk about things like the moon. The moon's big. Sure, Earth pulls on the moon, but the moon also pulls on Earth. We can see this because not only is the moon going around us, Earth also orbits slightly off its center. It's not actually, the moon and Earth are orbiting each other in a way. It's mostly in our favor, but it does exist slightly off from what it was. It's kind of what we get, or it's kind of the reason we have the tides. Earth pulls on the moon pulls on Earth. Questions about any of these three pieces, Newton's three laws? Okay. Then I want to take this example one step further. And I want us to write force-net equations for this object. So force-net equations. So a force-net equation, we said earlier, was the sum of all forces acting in dimension. Another way of saying a net force equation is a mathematical representation of the nice, lovely picture you drew. Okay? So when we write out a net force equation, what we're doing is we're summing the forces in one dimension. So I'm going to write in the x dimension. This is a net force. In the x dimension solely. What forces exist in the x dimension? Friction and the applied force. So if we're interested in the box, only the applied and friction act in the x dimension. So force applied minus force friction. Why did I just subtract force friction? They're in opposite directions, absolutely. So since they're in opposite directions, one of them's got to be negative. Doesn't matter which? No, not really. Equals mass times acceleration of the box. All right? Now I also need one for the y dimension. So force net in the y dimension is equal to the sum of the forces in the y dimension. Are you guys familiar with the sigma symbol as add up all the forces or all the values or summation? We've seen that before? Okay, good. What are my forces in the y dimension? Gravity and force normal. So force normal minus force gravity equals again ma. This a is in the y, this a is in the x. Okay, so all we're doing is we're writing out what are the forces acting on are on the object in each dimension. You'll notice I did not put anything involving force of the back box because it's acting on top. I did not put this force of friction or this force normal because they're acting on the ground. I don't care about them. I also did not put in this force of gravity that's pulling the earth up. I don't care about it. I only care about the forces that are acting on the box. Okay? All right. So, for the next one, let's make a slightly different example. Here we've got a wagon. Got some kind of cow. And here we've got the ground. I want to know, what does the free body diagram look like for the wagon? What does the free body diagram look like for the wagon? Take a moment, draw it out. What forces did you draw? How many forces did you draw? 4? Okay. What forces were they? Somebody give me one. Yeah. Applied force, or the cow force. Okay, that's 1. Next one. Gravity, 2. Next one. A normal force. Okay, last one. Friction. Where's the friction probably going to exist on this wagon? Like between what? So the wheels in the ground, probably not so much, because that's not going to really inhibit it. The wheels in the axle is probably where that friction is going to be. So any friction on this one is probably going to exist between the wheels and the axle, and you should have a free body diagram that looks roughly like that. Yes? Okay. How about the free body diagram for the cow? What's that going to look like? What forces should I draw here? Gravity. Let's always get the easy one out of the way. The other easy one? Normal. All right, now what else? Go ahead, Mark. The wagon applying a force on the cow. So force wagon. And I'm going to highlight those two forces, force cow and force wagon. Why am I going to highlight those? They're equal and opposite. Okay, and lastly, what other force can I put on here? Static friction, specifically. All right, so friction causing the cow to go forward. Because without friction, the cow stands there and spins his wheels. All right, questions on the free body diagram here. Okay, there's one last thing I want to add for us, and that's an equation for force friction. Force friction is equal to a coefficient of friction times force normal, but it is the absolute value of that. It's the absolute value of that because whatever negative or positive sign comes from force normal depends on if we decided force normal was in the positive or negative direction, which should not tell us anything about which direction the force of friction is acting. So the sign, positive or negative, shouldn't matter. So force friction is equal to coefficient of friction times force normal. Mu, this is the Greek letter mu. It's kind of like the letter U with a nosebleed. Is a coefficient of friction. And basically, it's the grippiness between two surfaces. Every pair of surfaces have a specific and unique coefficient of friction. They're typically determined experimentally. So the coefficient of friction between your tires and the road is different from the coefficient of friction between your shoes and the pavement. And of course, those values are different from the coefficient of friction that they probably felt yesterday. So along that line, I was thinking of putting up a sign this morning. I live on a roundabout. I was thinking about putting a sign that said mu is less than mu max. Drive with caution. But I figured drive with caution was too many words and it would take too long to read it. So I'm thinking mu less than mu max is a great sign to post along the roundabout to make sure people understand that it could be slick out.